Hello and welcome back to Casual Physics. This is video number 7 in the series on guesstimation, which is all about how to solve impossible problems, I like to say. If this is your entry point into the world of guesstimation, then I highly recommend going back to video 1 for the why of guesstimation and check out videos 2 to 4 for the essential tools and techniques that we're using throughout this series. Last time, we finished with a bit of a challenge for you to calculate how big the Pacific garbage patch is. Today, we are sticking with the ocean theme and asking ourselves a question: how much would the sea level rise if the ice caps melted? It's not only an interesting thought experiment, but it's a really helpful calculation to constrain your thinking around the effects of climate change. And that's because it represents the worst case scenario. Okay, how are we going to solve this problem? The core of this problem is recognizing that it's basically the same problem as me pouring this glass of water into this container and asking how high the water level would be afterwards. In this case, the tall glass represents the ice cap. It's got a small area, but it's tall. The container represents the earth. It's got a much bigger area, and so when we pour the water in, the height will be lower because the volume is the same before and afterwards. In physics speak, we say the volume is conserved during pouring. Now, let's turn this idea into mathematics and see what numbers we're going to need for our calculation. Volume before equals volume after is the simple expression for the conservation of volume. And it looks simple enough, but the detail is of course in, what is the before and what is the after. And we'll come to that in a minute. Before we do that, it's worth noting that even at this stage, we are using our guesstimation skills because technically the before is when we got ice. And anyone who's left a beer in the freezer for too long will know very well that frozen water takes up more space, more volume than liquid water. That's the kind of detail that, as always in guesstimation, we're trying to not worry about because we'll just end up in a rabbit hole and that will prevent us from actually doing a calculation. Okay, where does the height of the sea level come into things? It's in this volume after term. Now, if we imagine that the melted ice water is spread across the surface of the Earth, then that volume after is simply the surface area of the Earth multiplied by that extra height of sea level, and that's the thing we're really interested in. The key bit of guesstimation work is going to come from trying to figure out how much ice is in Antarctica. Essentially, what is that V before? And you won't be surprised to know that we are going to be making some more approximations. We're going to assume that Antarctica has no hills, no valleys, no crevasses. It's a perfectly smooth, regular prism like this. And that makes the volume of ice simply the land area of Antarctica multiplied by the depth of the ice. And so our problem becomes, 1, what's the land area of Antarctica? 2, how deep is the Antarctic ice? Let's start with the land area. I'm going to bet that just like me, you've never been to Antarctica, so you probably haven't got a good intuition about it. It's not helped by flat maps of the Earth, which make Antarctica look absolutely massive, and that's because it turns out you can't actually flatten a sphere onto a rectangle without distorting it in some way. Never fear though, we can cut through this distortion without even needing to resort to our favorite tool, the geometric mean. Let me show you. Approximately 2/3 of the Earth is water and 1/3 is land. Now we know that there are 7 continents, of which Antarctica is one. Although the continents are different sizes, they are not orders of magnitude different from one another. And so in typical guesstimation style, we'll assume that they have the same size. And that allows us to guesstimate that the land area of Antarctica is simply 1/7 of all the land area, which is 1/7 of 1/3 of the whole Earth. That's 1 divided by 21, which is approximately 1/20th, and 1/20th is 0.05, in other words, 5%. And so we've guesstimated that the land area of Antarctica is 5% of the whole Earth. And if we put this into our volume conservation formula, then something really nice is going to happen. You see we've got area of the Earth on both sides. That means we can cancel them out by dividing both sides by the area of the Earth. And now, if we tidy things up a little bit, you can see that all that's left for us is just to find the depth of the ice. And this is really cool because at the start, it looked like we were going to need to know 3 numbers: the area of Antarctica, the depth of the ice, and the area of the Earth. But because of the way we guesstimated the area of Antarctica, as a proportion of the area of the Earth, then we actually only need to guesstimate two numbers, and that is a massive win. And so the final thing we need is the depth of ice. And for this, we can use our favorite geometric mean if we have a sense of what the minimum and maximum depth are. What do you think? Pause the video, have a think. What is a reasonable minimum and maximum depth of the ice for Antarctica? We know that the ice can't be bigger than Mount Everest because that's the tallest point on the planet. That gives us a maximum of about 10 kilometers. The minimum is a bit trickier. I think it seems reasonable that the ice is at least 100 meters deep. Otherwise, drilling those ice cores from like thousands of years ago just wouldn't be such a big deal. And so the geometric mean is the square root of 100 times 10,000. That's the square root of 1 million, which is 1,000 meters, in other words, 1 kilometer. And when we put this into our volume conservation formula and do the usual mathematical jiggery-pokery, as I like to call it, then we arrive at a sea level rise of 50 meters. And so if the ice caps melt, we can expect the sea level to rise by 50 meters. Remember, this is the worst case scenario. Question is, how bad is that worst case scenario? Have a think. I encourage you to have a look at where you live. How far above sea level are you? Are you going to be submerged? Have a look. I'm going to take us now to Information is Beautiful. They've compiled IPCC and NASA data together to show just how bad things can potentially get. This is Information is Beautiful. They are a fantastic organization that compiles data visualizations on all kinds of things. This one is called When Sea Level Attacks, and they compiled information from a number of sources, IPCC, NASA, and others, and they look at, for a specific sea level rise, let's say 1 meter, which cities are going to be underwater. So 1 meter, Venice, gone. 2 meters, Amsterdam, Hamburg, St. Petersburg, gone. 3 meters, Los Angeles, San Francisco, Lower Manhattan, they are gone. 5 meters, my old home, South London, it's gone. 6 meters, Shanghai, Edinburgh, also gone. And 20 meters, New York, London, Taipei, they are gone. And remember, we guesstimated 50 meters, all the major cities are gone. And we can look at the top of the visualization here, 80 meters. This is the total sea level rise coming from the melting of everything, including the Antarctic ice sheet. The map of the world looks totally different, totally different. It's worth remembering that what we've done here is a guesstimate for the worst case scenario of all the ice caps melting. And, we're not in a position to say right now whether that's likely or whether that's unlikely. We're just trying to constrain our thinking around how bad that it could get. And it can motivate people to then do further research to think, well, what is the likely sea level rise? And just do more thinking on it. For some people, though, it's not important how likely this event is or not. They look at the worst case scenario and they say, do you know what? We need to plan for that worst case scenario. What if this happens? What do we do next? And for some people, their answer is to look to the stars and to seek a new home, Mars maybe, or even beyond. And so what we're going to do in the next video is we're going to kind of leave the planet and we're going to think about how feasible going to the stars actually is. So if that excites you, then come back for the next video. I look forward to seeing you there. And as always, thank you for your time and attention, and I'll see you next time.